In this second part of the three-part series on F256 kernels, we're here to talk about something that's a little bit, well, it's not necessarily top secret, but it's been a bit of a secret. Some time ago, I guess as review, a decision was made to move forward with something called MicroKernel for the F256 family of computers. And that put on hold OpenKERNAL. OpenKERNAL was intended to be a clean room version of the Commodore kernel, which had evolved from the Commodore PETs into the VIC-20 into the Commodore 64 that many of us know pretty well. It took a bit of a detour, and a lot of this was due to Gadget's inclination to reach further and implement some of what had been bouncing around in her head for some period of time to make something a little bit more modern that developers could harness and get more power out of, especially with regard to SD card support, TCP/IP routing, and other features that she had in mind. Well, here we are today to talk about a release that Gadget made available to the general public. It's available in her GitHub today. I'll include the link in the description below. So let's get started. Just have to get set up here. My Novation JCat. Let's see. Nah, talk about that next time. So to begin with, this is just a kind of a fancy cover, just for fun. But anyway, at the bottom here, you'll note that there are 39 vectors. These are the original 39 vectors of the Commodore 64, and to a large extent, probably the same exist in the Commodore VIC-20 and in the Commodore PET, though I haven't checked that. And I have these grouped by family, so to speak. And this is important because some of these are implemented in to a certain extent, and some of them are not in this version of the kernel. So we'll talk more about that in just a moment. But I'd like to start with what this is and what it is not. So while I read through my notes, you'll note on this first page here that *_kernel, it doesn't yet have a name. The original was OpenKERNAL. Then was the release of MicroKernal. There was a proposal to call this FNXKernal. Then it became OpenFNXKernal. So I'm not sure what it's actually going to be called, but I think the name will be settled out soon. But you'll see it's rather straightforward. To build, you should only need make and 64 tasks. Just type make, and it'll compile up for you, or rather assemble up. There's a caveat there in that my version of make, for some reason, or my version of 64 tasks, had some kind of a problem with regard to the debug level, and it just wasn't coming together correctly. But Gadget kind of chased that down and found out the current version is good. On the left side of the first page is the make file, which you can review. But this is the make file in full, and then we get into the code. It's organized. There's, I don't even know the number, but probably I'll say 15, 20 different source files to build this version of the kernel. But let me quickly dive into, kind of as an introduction, what this is and what it is not. So I have my notes here. I'll put them right in front of you. What it is, well, it's hardware support for the F256 family, including memory management, a memory management framework, and a lightweight CLI. It's not necessarily complete from a CLI perspective, but the beginnings are there, and most importantly, the jump table of commands, defining commands, is all there. So it's easy to extend. Memory management wise, this speaks to the way that memory management lookup tables are dealt with, and the way that Gadget is leveraging some of the flash pages which contain the SD code, which was open sourced, into use for this kernel. More on that later, but there's a fair amount of what I'll call the framework that's implemented as part of this kernel. What it is also, it's a handful of the original 39 Commodore kernel vectors implemented or partially implemented. And then most importantly, it's foundational support for the SD interface and for the Commodore IEC interface. So those are two somewhat tricky or thorny problems to solve in any kind of clean room kernel. Of course, it's based on code that was already published, at least from the SD support perspective, and I believe part of this was open sourced for the X16 project. So this is borrowed from that. And then the last thing that it is, from my perspective anyway, is it's a clean room. It's based on open source, as I said. It's available for use for your own projects, and it's available for use today. So feel free to run to the GitHub and get it. Again, the link will be below in the description. So that's in a nutshell what it is. What it is not, well, it's not finished. It does not so much as have a screen editor, it doesn't have a line editor, and it doesn't have a backspace key. So what it does support today, and from a CLI perspective, is the ability to type forward, and if you make a mistake, well, press enter and then type another command. There's a very small list of commands supported, but it has a couple things in there that are pretty handy. It's also not represented as being complete. So yeah, it's not finished, but it's also not really meant to be finished. It's meant to be kind of a start. Gadget took some care to make sure that it addressed the most important aspects of what a kernel would need to be, should somebody want to pick it up as a project and extend it. And I've had a good couple of weeks here to work on it. A lot of comments throughout, and there's little notes here and there about what you might want to do next. So you'll see that yourself as you kind of look through the source if you're inclined to do so. So while it does have a working open or file handle management construct, does not have, I said it does have, it does not have, I'll explain that in a moment. It does have a hard-coded single file load, and this load brings the IEC disk directory into $0801. So what does all that mean? It means that it includes a directory command, which I believe is dir. And the directory command, which I'll put on the screen up here, it pulls what is a basic program into memory at location 0801, which, just as luck would have it, is free memory for our use, as it was in the Commodore systems. And then it interprets that and displays on the screen the number of blocks, the file names, in a very familiar format. If you're used to doing a load, quote, dollar, quote, comma 8, and then list. I made one change to it, one enhancement, if you will, and that's to put the title of the disk and the ID of the disk in reverse field, just because I extended the character out routine to include reverse field attributes, so I may as well have done that to make it accurate. I'd like to say, I'm going to go back to this though, I'd like to say, to be clear, that it doesn't have a file open command. However, it has a load command. The load command, the kernel load vector, will load something at a fixed address, which is 0801, but that's easily changed, and I leverage that in a kind of an environment that I'm putting together. From an SD card perspective, it includes a ls command or a list command, if you're familiar with a Unix shell, and it's again a directory of the SD card. And there's as well, in the code you'll see it, there's as well a number of rename or unlink or remove to delete files off of SD. And of course the Commodore only needs a properly formatted string that's shot into the drive over the IEC port to carry out those functions. So let's get into the code quickly. It begins with, and again, I've created a header, colored header here, kind of by family, and I put the directory name at the beginning here. If anybody wants this, ping me and I'll find a place to put it online where it can be downloaded. So I can release it in PDF form, and then you can print it out yourself if you like. And you know, I just poked holes in this with a binding machine and threw a spiral binding around it. I just prefer to work this way. But so to begin with, on the platform F256 subdirectory, there's kind of the reading and definition of dip switches. And you can see on here, there are some things that'll be familiar to you if you've worked with the F256 before, such as Wi-Fi, a disk switch, a slip, a boot menu, yes or no to enable it, SIDs, whether they're present or not, and this is for the F256 Junior, which had sockets in it. So that's kind of a dip switch section. There's a section here which is really the core and the very valuable part of it, which deals with the memory management unit and which of the lookup tables are leveraged, in addition to making this code itself be auto starting. There's a signature, which is the hexadecimal, it's kind of funny, F2 followed by hexadecimal 56, which if you look at it together is F256. And this bit of text here, if pushed into one of the RAM slots that are scanned, will auto start by a portion of the kernel that gets the machine up off the ground. So this is very useful. And there's a description here that talks about each of the blocks that are read into memory, especially important for the SD code. This carries on for some time. I'll just go fast forward over this. FAT32 is the SD card kind of interface. And this is not a lot of code. It's certainly not complete code. It only runs up through about here, and there are some bits and pieces elsewhere. But this calls code that's in Flash on every F256 system that ships. So you already have the core of the code. This just does the calling of it. And you can see there are some things if you look through it. The open, the close, there's remove directory, make directory, delete for a file name, etc. And it jumps to FAT32 delete, for instance. So this is somewhat contained, but I believe it does some calls outside to other parts of this source, and it definitely calls into the Flash 8K banks that are banked in. Next is hardware section, which really just initializes the screen and the keyboard. And this is a vector which gets called from it, the IEC IO init, so that calls elsewhere. This is the core of the IEC code, which it goes on for some time with talk, listen. These are all kernel vectors that should be kind of recognizable to anybody that's been in or around the Commodore universe. I won't go through this. It's pretty detailed and a little bit hairy, but the good part is it's done and it works. So you merely need to call IEC out, IEC in, IO init to use the functions. You don't have to understand it or make any changes to it. In fact, I would recommend against getting into any of this code to make changes to it. You'll notice here there is some sleep, 20 microseconds in here, right, in some places. And this may have been required based on the old school timing of the IEC bus versus a 6.29 megahertz 6502 that's running. So some of these protocols are very persnickety or specific in terms of the tolerance for changes in timing. But Gadget's taking care of all of it for us. There's an interrupt definition, which goes into the standard RQ that runs and leverages or latches to the Vicky RQ timers for doing things like scanning the keyboard, etc. And then we get into kind of keyboard support, starting with the Commodore keyboard support. And this is the native VIC-20 or C64 keyboard. She says C264, so that's interesting. Maybe, I think the C264 might have been one of the TED machines, but in any case, maybe it was just a typo. In either case, it takes care of all of the complex interface adapter 65022 chip, which is kind of sending out pulses on one and reading from another bank to see which keys in the 64 key matrix is pressed. So where those cross points occur, this code detects it, and then through a table puts characters into a keyboard buffer that gets scanned and maintained by the RQ. So you'll see some nomenclature here having to do with constants, with values of all these various keystrokes, and I've redefined a number of these because some of these are based on, at least on the PS2 side, based on Emacs bindings, which is something that occurs in the Unix land. And I'm moving it back to kind of more of like a Commodore-esque type of interface, at least for my own personal use of this. The second keyboard supported is the F256K, which is I believe, an 8x9 matrix. It's a little different than the original matrix. Of course, this is the 20 pin that's, I have it handy? I have it handy. This is the 20 pin interface that is available on the Junior that you can plug your own Commodore keyboard into. So this code scans for that keyboard, which is nice. This code scans the F256 keyboard, which is very similar, but it uses second 6522, I believe, on board the F256K board, and it does likewise scanning, and then of course has its own table for lookups and does something similar. And by the way, I believe, haven't tested it, but I believe that this will work simultaneously, where you can have a PS2 keyboard in a Junior in addition to a Commodore keyboard in the Junior, and type a letter on one, type a letter on the other, and they'll both go into the queue next to each other, which is interesting. At least I believe that's the intent, but I'll have to get around to testing it. And it kind of comes together here in this keyboard source. And then we're on to the screen. So screen is one of the more important aspects of any kernel, and what it does is it allows printing of characters to the screen. It allows you to kind of maintain the confines of what is an 80 by 60 character screen, such that when you get to the bottom, what happens? Well, you press enter or you move cursor down ideally, and it scrolls up and the color map behind it scrolls up. So that's what this routine does, and you'll see something here called getCH or putCH. And if you know the some of the hardware registers, you'll know what's going on here with I/O control, using some zero-page addresses to move a fair amount of data around the screen. Variables or bytes for row and column, which are key here. The plot function, which is embedded here somewhere, and what plot does is it lets you read the screen. Where's the cursor? Oh, it said column 6, row 17. Oh, I want to set it now. Set the cursor, so you can clear the carry flag and push the cursor to someplace using the plot function. That's another kernel routine called plot, P-L-O-T. So that's here. There's something here about a device, which I think goes through, and it doesn't do a lot, but it's probably dev state, REQs, fetch, allocate, free, install. This is probably all part of setup again. I haven't really gotten into this piece of code yet, but it's pretty brief. Then we get into the PS2 keyboard driver, which is next here. You'll see some of the same business. It goes on into actually 2 pieces of source. You've got the same thing here with the alternate control key, meta keys, so to speak. Here's tables of the keys and what the key codes, which are, of course, PS2 key codes, map into from a character perspective. And there's a kind of a key map here, which may be familiar to anybody that's worked with PS2 in the past. Easily changed. Then we're onto the command line interpreter, the CLI, and this is I think in 2 pieces. And you can see through here there's a list of all of the verbs that are supported, and you can see a couple of them are commented out. Load is commented out, run is commented out, but the intent was to have it so you can run something at a certain address, var exec, run it at an address, and we'll talk more about that later. That's not part of the current build of this. But it does do a SD directory. It does do a IEC directory. It will list the program in memory, which is to say, list the directory that was read in from a Commodore device. Change the drive number to drive 8 or drive 9, and help, which displays some text, which is around here somewhere, probably in the next piece of code. So that's more on this later. The list, CLI list, I believe, is responsible for listing out the Commodore disk directory from the IEC drive. So you can see it's checking for a token. It's printing the number, which is probably a number that's number of blocks, and it continues on. It's relatively straightforward. It ends there. Then you're down to vectors, which includes the definitions of the 39 aforementioned Commodore entry points for kernel calls. And some of these have been renamed slightly, I believe. And I think I corrected them for this first page. But something like ACPTR is renamed for, that's to receive, I believe, off of the IEC bus. So that I think might be called IEC in. I think she renames it too. Just little changes here and there. And there's not much more than this. There's a core error assembly. There's IEC, just kind of some setup. This is where the actual module gets linked to, having to do with namespaces inside of 64 tasks. You've got a fairly extensive IO.asm, which includes a lot of the IO, the ones that are coded so far, like set LFS, which is the logical file handle, the set name, which allows you to set a file name for the IC device, the load command, which I mentioned is hard-coded to load at 0801, specifically for the disk. There's a save command, which I have not tried yet. And there's a bunch that are not implemented here. You can see them called out in lowercase: open, close, check in, check out, clear channel, and close all. Open, close, clear channel, and close all are pieces of code that maintain a table of possible files being opened at any one time in memory at a certain specific location in memory. And it's in such a way that there's error checking inside of the Commodore kernels. The way it works is it kind of scans to make sure a file's not open already, a logical file name or number, I should say. If it is, it says, oh, file open error, right? You've seen all these messages before. If a file is closed in between, there's code that shifts that table down to keep it such that it's stacked from 0 upwards. And some of these, like clear all, will clear all of them. There's others. There's plenty here and plenty to do, plenty of work to do. And again, not all of it is really required based on what your idea is to use this kernel. What would you use it for? This defines memory top, memory bottom. This is not so important. Of course, basic, if it was running in a ROM, would probably look to see how much memory do I have as basic and then leverage it. But we're not running basic here, although we can. One of the first things I did, by the way, real-time clock, RTC, which has the set time and read time, and there's also an update time call, which looks like they're not implemented. In fact, it says, fill me in, use the RTC, RTS. So this is one of her notes to say, well, I didn't get to this yet. There are three kind of timer based: is set time, read time, and new D update time. But those aren't written yet, and those are fairly straightforward. So there you have it. I'm going to give a demo of this in kind of native form as assembled. We'll see what it does and what it doesn't do. And then in the next video, which is part 3 of this 3-part series, I'm going to demonstrate my version of this, which is enhanced to some extent. And we'll talk about that more next time. I do want to give an advertisement for 2 really good books. The first one is a book called Inside the Commodore 64, written by a gentleman named Milton Bathurst. And I think this was done in Finland or somewhere in Scandinavia, I'm not even sure, in the 80s. And it is a fully commented, this is an original copy. Actually, this is one of the earliest copies. In fact, most people have seen this. It's in a bound form. This is not. This is in kind of spline punched form. And I think these pages are hand cut, which is kind of crazy that somebody cut these in like probably a slice or a couple pages at a time. But it's a fully commented ROM of the basic ROM and the kernel ROM for the Commodore 64. Every single line is lookup tables, cross-reference tables. It's really an amazing resource. And I'll put a link to the archive.org version of this book. But you can look up something like close and Commodore close command, and go to the piece of code FFC0 and see what it actually does, line by line by line. And then from here, the second book or the second plug is mapping the Commodore 64, and this has been beat up. This is my original book from when I was a kid in the 80s, and Sheldon Lehman, this is part of the Compute Books Press. This is invaluable. You can look up an address, it'll tell you exactly what it was for. Certainly the earlier parts of memory are for shared between kernel and basic. Memory map is similar because it's 6502 based to what we're used to here. And then in the end, you have a section on all of the kernel routines and what they actually do. So that's kind of handy as well. So I wanted to at least mention those 2 books. Oh, finally, this book here, which some of you have seen or have, it's 10 print. It's a lot about kind of that famous one-liner at this point, a piece of code that first appeared in one of the Commodore manuals. And it talks about mazes and theory and a bunch of other things. It's a pretty good book. But the point is that I'm taking this program, and in a subsequent video, I will take this kernel as it is, in its kind of unfinished form, bind to it a basic ROM that I download off of Zimmers, Zimmers, and run this program as it is. It's going to look a little different, but it behaves pretty much the same way, even though it's completely unfinished. So it's interesting. I have to hand it to Gadget for getting it to the point where she can, plug a basic ROM into it and actually build it, and it'll run some of the programs. Of course, it's largely unfinished, but a lot of it's there, and there's great things to come. So stick with us, and we'll talk soon.